Analytical Chemistry 1, Lesson 53. Each titration is unique, adjusting the pH, the temperature, the amount of indicator, the concentration range. There's definitely some individual art mixed in with the science. There are some general directions, however, that can help the new researchers, such as yourselves, to get started in the field and to be able to understand the work that others are doing. There are 4 fundamental titration experiments that we will now describe. The first is called Direct Titration and is the experiment we have been working with throughout the class. We have analyte and we titrate it directly. With these EDTA titrations, we now know that we must buffer the solution appropriately and choose an indicator that works well in that range. Auxiliary complexing agents may be necessary and used here when needed. So here's a question that you could be asked involving a direct titration. A 10 ml aliquot of a solution containing copper 2+ is prepared for an EDTA titration by buffering it at pH 9.5 and adding sufficient ammonia that it is 0.1 molar in ammonia. A couple of drops of the pyrocatechol violet PV indicator is added. The EDTA solution has a concentration of 0.07982 molar and requires 12.45 milliliters of titrant to reach the PV endpoint. What is the concentration of copper in the sample? Now, the actual math associated with these titration questions is in fact rather straightforward. It is not complicated. What is hard is sorting through the question, identifying the information to be ignored, and finding what you need, and doing some simple multiplying, dividing, and adding, subtracting. So think carefully about what you need and what is relevant in the question for that target. In this question, we want the concentration of copper ion. All that stuff about the indicator, the pH, the auxiliary complexing agent are things that you do not need. They were necessary for the experiment, but the question declares the value of the endpoint, and that's all you really need to know. Moles of EDTA to reach the endpoint is 9.938 times 10 to the minus 4 moles. Because EDTA titrations are always with a 1-to-1 stoichiometry, this must also be the moles of copper in the original sample. We know the original volume was 10 milliliters, so the concentration of copper was 0.09938 molar. Because the stoichiometry is 1-to-1 for EDTA titrations, it is also basically just a C1V1 equals C2V2 calculations, because moles of EDTA must equal moles of copper. And that's just what a CV calculation gives. Well, this is the most straightforward titration and calculation. We have to do a little more thinking with the next ones. Sometimes conditions are such that the analyte precipitates in the absence of EDTA, or it may react very slowly, making the titration difficult to complete. Or the analyte may block the indicator, meaning that the EDTA is not able to displace it and bind to the last bits of the analyte, and then the endpoint is not observed either. Now, we can deal with many of these problems by employing a back titration. We add a carefully measured amount of EDTA. By previous experience or knowledge, we know that this is an amount in excess of what would be needed to reach the equivalence point. We just do not know at this point how much in excess. After adding the EDTA, all of the analyte ion is now in the coordinate complex with EDTA, and there is unbound EDTA as well because it was added in excess. Since we know how much EDTA we put in, if we knew how much did not react with the analyte, then by subtraction we could know how much did react, and therefore how much analyte was present in the sample. We titrate the excess EDTA with a standardized solution of another metal ion. The second metal ion must form a weaker EDTA complex than the first so that it does not displace the original analyte. Here's a problem to describe this situation. To a 25 milliliter aliquot of a solution containing nickel 2+, we add 10 milliliters of a 0.08251 molar solution of EDTA. After adding the appropriate indicators and buffers, we titrated to the Zincon endpoint with a 0.02262 molar solution of zinc 2+, which required 11.51 milliliters. What was the concentration of the nickel in the original sample? So look in the question for the substances that are actually measured. Look for what you actually titrate. Then decide how it relates to the other substances of interest. In this case, the titration you perform is actually with zinc ion. Your burette does not have EDTA in it, just a well-calibrated zinc 2+ solution. In setting up this experiment, you would have wanted to make sure that the zinc does not displace the nickel that originally reacts with the EDTA. By looking up their formation constant values, we see that zinc is smaller than nickel by about a factor of 100. So this experiment should work okay. The amount of zinc titrated is 0.2604 millimoles. Your chemical insight needs to be employed now, as you recognize that this must be the same as the amount of EDTA in excess of the amount needed to combine with the original nickel analyte. This hinges on knowing that these EDTA complexes are 1-to-1. Otherwise, a different stoichiometric ratio would have to be invoked. But that is one nice simplicity of EDTA titrations, that they are all 1-to-1. Think chemically again. We want to know the nickel concentration. The amount of nickel is related to the amount of EDTA that it reacted with. We know how much was left over. What we now need to know is the total amount added originally. That amount is found to be 0.8251 millimoles. Using the amount we know was left over, how much combined with the nickel? Well, we find the EDTA that reacted with the nickel analyte must be 0.5647 millimole. And since, again, the stoichiometry is 1-to-1, this is also the moles of nickel present in the original sample. So what was its concentration? Well, the nickel concentration was 22.59 millimolar. Now this experiment has 3 different volumes that are used. The volume of the original aliquot, the volume of added EDTA, and the volume of titrate. Make sure you keep them straight. It's easy to confuse them. Keeping the numbers clear in your head is the real challenge of these questions. Let's look at the next type of titration. There are instances where certain ions do not have an acceptable indicator. The mercuric ion Hg2+, and silver Ag+, are a couple of such examples. Experimental conditions may impede appropriate endpoint detection for other ions as well. A displacement titration allows us to shift the analytical signal from one ion to another. With the target analyte ion in solution, we add another ion already bound to another ligand. The key here is that the interaction of the first ion with the added complex is such that it can stoichiometrically displace the new ion, which is then titrated with EDTA. The key here is to ensure that the original analyte is replaced by a stoichiometric amount of the new metal ion, which is then titrated. Here is an example problem. To a 25 milliliter aliquot of a solution containing chromium 3+, we add an excess amount of magnesium EDTA 2-. We titrate the magnesium that has been displaced by the chromium with a 0.06245 molar solution of EDTA. The titrate volume required is 22.13 milliliters. What is the concentration of chromium ion in the original sample? A couple of things to note. We are adding a metal which is already complexed with EDTA. There should not be any free magnesium, beyond that released because the complex has a finite formation constant, nor any free EDTA with the same proviso in the added solution. Also, we do not need to know the precise amount of the added magnesium complex. We just need to know that it has been added in excess of the chromium. How do we know the chromium will displace the magnesium? Well, take a look at the formation constants. The chromium complex is much more stable than the magnesium. It will readily displace the magnesium ions. At this point, all of the chromium should be bound in an EDTA complex, and all of the magnesium should be free in the solution. We can now titrate with our standard EDTA solution. The amount of EDTA delivered in the titration is 1.382 millimoles. The key chemical insight we need here is to recognize that the EDTA amount must be the same as the liberated magnesium amount. The 1-to-1 stoichiometry plays out here again. But furthermore, the magnesium must be the same as the amount of chromium in the original aliquot, again because of the stoichiometry. So the concentration of the chromium was about 55.28 millimolar. The math, again, is very easy. Just keep your chemical wits about you. One last word. The ligand undergoing transfer does not have to be EDTA. It can be anything which has a stronger affinity for the analyte ion than for the added displaced ion. Watch for this because the stoichiometry may no longer be 1-to-1. Use your chemical insight to scale things appropriately. Another approach to titration is an indirect titration. So an indirect titration is useful for measuring anion concentration rather than cations, as we've done so far. In particular, carbonate, sulfate, sulfide, and chromate have been measured in this way. The process involves first a precipitation, followed by a titration. We need to watch the stoichiometric relationships here. One approach uses the precipitate, while the other uses the filtrate for further analysis. In both cases, we precipitate out the anion with an excess amount of an appropriate metal ion. If we are to use the precipitate, we do not need to know how much precipitant was added, just that it was in excess. If we are to use the filtrate, we do need to know the added amount, a metal amount, precisely. If using the precipitate, we filter and wash it, and boil the precipitate in excess EDTA to redissolve the precipitate and bring it back into solution where it binds with the EDTA. The excess EDTA is then titrated with a standard metal solution. Knowing the differences allows a calculation of the original concentration. If using the filtrate, we filter and wash the precipitate. Be sure the wash water is added to the filtrate. And the excess metal ion in the filtrate is titrated with EDTA. So here's an example problem. To a 25 ml aliquot of 0.04332 molar solution of copper nitrate, we add 15 milliliters of a 1 molar acetate buffer at pH equals 4.5. We pipetted into this solution 25 ml of our analyte solution containing an unknown amount of sulfide. The copper sulfide precipitate was filtered and washed with hot water. To the filtrate, which is everything except the precipitate, we added ammonia until the blue color of the copper tetraammonia complex was observed. Titration of the filtrate with 0.03927 molar EDTA required 12.13 milliliters to reach the Murexide endpoint. What is the concentration of sulfide in the original sample? Now you'll notice that this question has a lot of accurate but confusing details. You need to learn to look beyond that to find the essential elements of the question. In this case, we are analyzing the filtrate. The original copper 2 plus was 1.803 millimoles. The unknown amount of sulfide was precipitated out as copper sulfide. Now note the stoichiometry is 1 to 1. The copper was in excess, so we determined the amount of excess copper by titration with EDTA. The amount of EDTA is 0.4763 millimoles, which is the amount of copper that did not react with the sulfide. The amount that did react is the difference with the amount added originally, or 1.327 millimoles. And this is the amount of sulfide in the original sample. Hence, the sulfide concentration was 53.07 millimolar. As you can see from all these different titration techniques, our ability to accurately measure the concentration of metal cations and many anions with EDTA methods is quite extensive. When analyzing a problem, just keep track of the chemistry, watch the stoichiometry, and don't get lost in the details, and you can find the answers. A final technical trick is not another titration itself, but is that of masking. This is used in situations where there are 2 or more metal ions in solution and we seek to know the concentration of each. A straight EDTA titration would measure the sum of the metal in solution. Masking involves adding another ligand that preferentially forms stronger complexes with some metal ions than does EDTA. An EDTA titration then only measures the unmasked ions. Cyanide and fluoride and triethanolamine are examples that can be used when the right ions are mixed together. A mixture of magnesium 2 plus and aluminum 3 plus can be titrated by masking the aluminum ion with fluoride. First titrate the mixture for both for their sum, then titrate the magnesium alone by masking the aluminum. The difference provides a measure of the concentration of both. A mixture of cobalt 2 plus and calcium 2 plus can be analyzed separately by using cyanide to mask the cobalt ion. And demasking can be a useful tool. The addition of the right chemical agent can release the masked ion from its strongly bound ligand. For instance, formaldehyde can react with cyanide to release metal ions bound to it. Subsequent EDTA titration can analyze the unmasked ions. So, lots of tools, lots of smart ideas. Your chemical intuition will allow you to navigate all of these strategies and use them to your analytical advantage.